Hello, everyone. Good morning, good afternoon, and good evening, depending on where you are. My name is Ruchi Soni, and I'm a Senior Energy Access Specialist at Sustainable Energy for All. I'd like to welcome you all to the first webinar of the year that focuses on open data and analytics towards achieving smart electricity access planning. We're very pleased to be hosting this interesting discussion today on behalf of the Mini Grids Partnership. I'll introduce the partnership in a minute. But just to introduce our panelists, I'm joined by a great set of panelists, including Andres Gonzalez Garcia, CEO of Evolution and researcher at MIT and IIT Comilas Universal Energy Access Lab, Andrea Salberg from KTH Royal Institute of Technology, and Navin Rajgare from TFE Energy. My role would be to play the easy part as a moderator for this discussion. If the registration numbers for this webinar are any indication of the interest, especially in this busy January period, we've had a great response of over 200 people who have registered. So many thanks to everyone who's tuned in. Before we jump on the presentations, I'll provide a quick overview of the Mini Grids Partnership. The Mini Grids Partnership, or the MGP, is a consortium of over 330 mini grid stakeholders in the space with the common goal of enhancing and complementing each other's work through collaboration and coordination. It serves as this umbrella group to bridge different stakeholders and initiatives, especially those from the industry, government, and investors or donor community. In a nutshell, the MGP offers the market infrastructure for the mini grid sector. In terms of our activities, the MGP convenes a global network, hosts working groups and regular calls with the steering committee members, and events with the partnership members. It also publishes industry newsletters and hosts webinars, such as this one. SE for All serves as a secretariat for the partnership, and I would strongly encourage you to check out our resources on the website at www.minigrids.org. Can we move on to the next slide, please? A little about the webinar itself, where we're talking about the various tools and platforms available for energy planning and open data analytics that is an important aspect underpinning this planning. As many of us already know, the first step very often is for the government stakeholders to know and understand and map where unelectrified and under-electrified populations reside, what kind of electricity access they may already have, and by what means can they be provided with this access. This in turn is complicated by the fact that there is either lack of data or data often being of poor quality and being fragmented when it's available. This is where the tools for electricity planning come in. These tools enable accurate and dynamic infrastructure planning. They help estimate the cost of electrification for households, businesses, including for mini grids, that being one of the elements of today's presentations that our panelists will focus on. In addition, these tools also help in other parts of the value chain in the sector. To name a few, these include enabling strategic decision-making for different stakeholders, helping identify opportunities and informing investments, also in policy and regulation design, and finally assisting the private sector in their decision-making. I'm pleased to have the fellow panelists join me in this discussion to discuss this in greater detail and talk about the respective tools to better support the sector. Lastly, before handing it over to Andres, just a quick note on the webinar process. Following the panelists' presentations, we will have a question and answer session where the panelists will directly respond to your questions submitted by the audience. If you would like to ask a question during the webinar, and we really hope that you do, please type it out in the question answer interface at the bottom of the screen. With no further ado, I'll hand it over to Andres Gonzalez Garcia, who will speak about the Reference Electrification Model. Over to you.
There I am. Sorry, I was in mute. Well, thank you very much, Ruchi, and thank you for all the attendance for getting into this topic, which we are so passionate about. Well, as Ruchi said, I'm a researcher, affiliate researcher at the MIT Institute of Technology at the Energy Initiative, together with the Institute for Research in Technology in Madrid. We started running the Universal Access Energy Laboratory 12 years ago, and trying to put into action our many years of experience for the power sector, especially in modeling, but not only modeling, but regulation and business models, so to be able to accelerate universal access. Well, next slide, please. Well, this is one of our projects of planning, which is the purpose of this talk. Here is the plan, Universal Access Plan for Rwanda 2024, which we have developed, and it was approved last April 2019 by the government, and resulted in, well, the small figure of $1 billion, well, sorry, $1,000 million, $1 billion US dollars, which is the amount of investment which is required to achieve 100% electrification at least cost options, meaning that part of it, 52% is going to be grid extension, around 10% would be microgrids covering more than 200,000 customers, and then we would have the rest, around 38%, would be solar kits or standalone systems. So to do this, we actually use the Reference Electrification Model, which we have been developing for the last 6 years. Next, please. Well, we start with the spatial pre-processing of everything that has to do with location of multiple clients, not only domestic, but productive and community. We use their individual locations and their individual profile loads to find out what's the best system that could be used to provide them. Then, of course, we work with the position of the lines, whatever energy resources are at hand, whether we use street maps, administrative boundaries were required by the concessions. Well, next. With that, we are able to respect topographic features, like in this case, well, we have, next please. We have an example of our research in a project in Indonesia, where we have developed the electrification plan for the Maluku Islands and Papua region. And here you can see how the model to reach each one of these households that we want to electrify can either choose microgrids, which are all these suns and green lines around the wide area, and also can decide to extend the network, which in this case is the black line at the bottom picture, where you would extend the red lines, which is medium voltage, and the blue lines, which is low voltage, to reach each and every household. So it decides and compare each option for every household, so to decide whether it should go together with other households and whether it should be connected as a group to the network, or otherwise be left isolated or in a microgrid. Next, please. So here goes one of the important things. To determine what's the least cost options, what we do is actually design each one of these systems. So we calculate millions of options using, of course, intelligent searches and AI to determine which are the systems which are actually preferable to fit each one of these customers according to its characteristics. So next, please. In this slide, you can see at the right of the image a bunch of grid extensions, extension 2104 or extension 220. This is the least cost option for the electrification of a certain cluster, a certain village, a certain group of customers. And that's the blue line. Then the green line is the equivalent cost of electrification with a microgrid. And we compare both. So in the dark blue line that we have from up, left to down, we have the ratio of the cost of electrification between grid extension and microgrids in this case. So whenever it's cheaper to extend the grid, we would choose a grid extension. When this ratio becomes 1, we would have, okay, it's equally expensive to build a microgrid or to do grid extension. And from that onwards, which is all the projects labeled UG 330 and on, from there on, microgrids in this case, which is Uganda South Service Territory, win, and not by a small fraction. We start winning by 20%, 40%, 50%, so 5 times at a certain moment, it's 5 times cheaper to build a microgrid than to extend the grid. And there is where our model stops comparing and assumes that everything that is farther than that will be at least 5 times or more cheaper. So we decide microgrid in this case. Next, please. Well, with this, we are able to design these systems with a granularity of customer level, and meaning that in a certain village, as that one that we have in the right corner, we may have some microgrids, we may have, which are the green lines, we may have isolated customers corresponding, taking into account how distant are they from the center of the village, or how distant are they from each other, and how much they consume. Next, please. This is an example of the least cost solution for the self-service territory in Africa, in Uganda. And there you see that for a piece of territory which is 60 kilometers wide and 40 kilometers north to south, we find there is a lot of grid extension, but there is also a lot of microgrids, and there is also a lot of small isolated systems. Distance is not in our case, as in many others of the tools that we are seeing today, because in this distance is not the only proxy. So you may see microgrids almost under the grid, meaning that a community with 50 households consuming 150 watts each maybe not be worth the cost of medium voltage, low voltage transformers that would connect it to the grid, whereas other clients with some productive activities that might be 5 kilometers or 10 kilometers from the grid would be electrified with grid. So the comparison goes system by system, and I want to emphasize that. If we compare this least cost solution next with another proxies that are being in use, for instance, in Uganda, in this same country, the approach followed by the government was, okay, we want to electrify every household with a connection cost of $2,000 per customer or less, calculating net present value. With this algorithm, you see that there is a much more grid extension. And okay, that's a political choice, but what we want to emphasize is that the cost of this solution is 30% more costlier than the previous one. And that doesn't mean that it's going to have a better service. For instance, their central network in Uganda has 85% reliability in average in rural areas, whereas the microgrids may reach 98 or 97 in the designs that we did. Next, please. And if we compare that to business as usual 100% grid extension or 98, which is sometimes also the purpose of some agencies, we see this is the map that we would get, and still the cost would go still higher, up to 150%. We would have some connections here that would be over $14,000 per connection. Okay, next. I want to keep my time into this 10 minutes, so I have a little left. We do this not only designing the network and running the power flow, so every component is designed with the catalog and the low voltage and medium voltage rules of the country, but also calculating the generation with the hourly dispatch through a whole year, considering all the resources. So we consider the demand of the different customers in the microgrids added together. With that, we develop the dispatch. It's a Homer-like generation problem. And with that, we can also provide measures of quality of service, which is the picture at the down right of the image, where for every hour, we know how much reliability we are providing. In this case, we are providing almost 100% reliability anytime from 9 in the morning to midnight, whereas in the night it goes down as the batteries are exhausted. Of course, we can design with any kind of restrictions in this regard. Next one, please. So this is an example of different designs of different sizes of microgrids. This is just a sample with their different profiles of reliability and the different dispatch for sample days in the year. And at the left, you have, in this case, which is Rwanda, what is the cost of the different grid extensions and microgrids that the system has calculated to develop this least cost plan. This enables the country to not only plan their investment and their pipeline of projects, so we work also on the implementation of these projects. So we prioritize, for instance, the ones supplying productive loads or community loads, which in this case are the ones at the left of the pipeline of projects because they have more average consumption, and it's logical that they have less cost per kilowatt hour, which is the green lines in both cases. An important thing here is that we always talk about the cost of per kilowatt hour, which is not at all at any rate constant. We have costs which are under 20 cents or 15 cents or 12 cents at the top left of grid extensions, but some grid extensions go as high as 80 cents per kilowatt hour, the ones which are in, but still they are least cost. Whereas microgrids in this case start at around 22 or 25 cents per kilowatt hour, and again climb up to 80 cents. So our main message here is that microgrids and grid extensions are not two sides of the same coin. And if microgrids are grid compatible, microgrids can be a least cost option to begin with. And in the event demand rises or the cost of grid extension diminishes, or the reliability of the central grid improves, they may become connected at some point later. And next. With this, I'm handing the floor to Andreas Salberg. Thank you.
Okay, thank you. And thank you all for joining here. So my name is Andreas Salberg. I work with geospatial electrification modeling within the team at KTH Royal Institute of Technology in Stockholm in Sweden. We work with the development and the application of the open source spatial electrification tool, or ONSET for short. So next, please. So ONSET is an open source tool. You can find it through our GitHub page or through our website. So anyone can download it and use it to run their own electrification scenarios. So what ONSET does, it looks at how to increase access to electricity through a combination of grid network extension, mini and microgrid systems, and standalone systems, so solar home systems. So to know for every settlement which kind of technology should be used, we draw on spatial data. So we identify where the population is, how it's distributed, and for each settlement, what are the energy resources that are available. So how much solar, how much wind, is there hydro available, and so on. But also how far is the settlement from existing grid infrastructure and several other factors. So we've used this tool to generate electrification analysis both on a regional scale, so all of sub-Saharan Africa, for example, but also for in-depth country studies where we work closely with local and international stakeholders to ensure that we have access to the best available data and that we develop scenarios that capture the local context and challenges. So next, please. So what we do in the ONSET tool is that we divide the country into settlements. So these are the colored clusters that you can see on the map here. And the size of these clusters can range from a few households up to entire cities. We then draw on information from approximately 15 geospatial datasets and 150 input variables such as the population growth projections, the technology costs and their characteristics. And we try and determine which is the least cost electricity generation technology for each and every settlement. So for each settlement, we calculate the cost of grid connection, the cost of different types of mini grids based on different resources, and the cost of solar home systems, taking into account both investments, operation and maintenance costs, and fuel costs. And we then choose for every settlement the technology that we find can generate electricity at the lowest cost for that settlement. So the color you see of the different settlements here represent the different technologies that would provide least cost electricity in this case. So if we go to the next slide. So today I'll show some example results that are available at the World Bank's and SMAP's Global Electrification Platform, or the GEP for short. So the GEP is an open access platform where we can first of all browse through electrification scenarios. So currently there are 216 scenarios per country for 46 countries available on the platform, which have been generated using a version of the onset model. And these explore the least cost electrification options for different demand targets, different technology costs, and some other aspects. Hopefully we'll increase the number of countries, but also see results here from other tools and other models in the future. So from this platform, you can also download the input data that we used and the onset model, and you can run your own customized scenarios with your own costs and assumptions if you want to. So if we go to the next slide, we'll look at a few scenarios here for Angola. So Angola had about 42% access to electricity in 2018, and we're looking at how to go up to 75% access by 2025, and from there on to 100% access by 2030. So in this first scenario, we're looking at supplying quite low levels of electricity access targets. So low consumption per household. So the map here shows where the different technologies can provide least cost electricity. So we can see there are the larger blue settlements in central Angola, where grid connection is the least cost option. We can see that in the red circles in eastern, northern, and southern Angola. In the darker shade of yellow, mini grids could supply least cost electricity. And for the smaller settlements that are bright yellow, solar home systems would provide least cost electricity in this scenario. And on the right-hand side here, you can also see the share of the population that would receive electricity by each technology on the national level, as well as the aggregated investment requirements to the bottom right. So if we go on to the next slide, if we run the same kind of analysis, but in this case, we have a higher demand scenario. So assuming each household will consume more electricity by 2030, we can see that the technology mix changes. So we see a higher share of grid extension, and we also see a higher share of mini grids in this case. So there's a lot more blue in the central parts of Angola, where the grid network gets extended as the least cost option. And we see an increasing number of mini grids in the remote areas of Angola. So we'll look at one more scenario here in the next slide. So we can also say, what if we target high demand, but we put some restrictions on how much the grid can be extended until 2025? So which could be the case for a number of different reasons. So now we see the results here for 2025 on the map. And we can see that there's actually a lot of mini grids also in central Angola in this case to supply least cost electricity, as the grid is limited, so it does not expand in the first time step. But when we move on to 2030, so in the next slide, we see now the grid gets extended to those settlements eventually. So here we can start to think about the different implications this might have, as we have some mini grids that are eventually connected to the grid, but we have some mini grids in more remote areas which remain off grid even by 2030. So if we move on to the last slide here. So I just wanted to end with a few remarks on these results and how we use the onset tool. So first of all, these results focus only on supplying residential demand. As we move forward, we plan to incorporate also other demand sectors such as agriculture and productive uses. And we know that these are important, especially as we look at mini grid locations. Also, it's important to note that Onset chooses the technology for each settlement based only on the lowest levelized cost of generating electricity. So it does not directly take into account, for example, ability to pay or the financing availability for different technology options which need to be, or which you can work into the different scenarios if you develop them. So the Onset tool takes anywhere from just a few minutes to a couple of hours to run a scenario using the Onset tool on a regular laptop once you have collected all of the data. And the running times depend on the size of the country and the number of settlements. So we think that this tool is well suited to do quick screening analysis of electrification options in an area or a country, and also to explore the effect of different demand levels, what happens in different cost trajectories for different technologies, and so on, and provide a high-level perspective of electrification strategies. And finally, we believe strongly that we can get the most useful results and analysis through collaboration. So combining our expertise that we have in the tool and how it works and how it can be developed with the expertise of others of local contexts, challenges, and data. And we also try to keep regular capacity building events together with international stakeholders to train others to use these models. So that's it for me. Thank you.
Hi, everybody. This is David Razgere. I lead Village Data Analytics project here at TFE Energy. Thanks for everybody for joining in the webinar. So Village Data Analytics is a software-enabled service which automatically detects all off-grid villages and determines if those villages are suitable for either mini-grid-based electrification or solar home system-based electrification. As you see at the right side, we actually analyze a bunch of satellite imagery to extract information about these remote communities. Then we infuse, a bi-level GIS data that might be available in the market, and also add in any sorts of customer data, and we infuse all of these data together to make a data-driven decision-making tool so that it can really define what sort of electrification needs to be done in which particular village. Next slide, please. I think the best way for me to explain what VIDA does is through a case study. So I will quickly go through a VIDA analysis from the northwest part of Nigeria, near Sokoto. What we will focus is the area within this red box. It is 10,000 kilometers square of area, and it is likelihood that there are about 1 odd million people living in that particular area. You see at the bottom there are 4 different steps that Village Data Analytics uses. First is Village Data Analytics automatically identifies off-grid villages. Then it extracts information from all of these identified villages, separate information from all villages. Then those informations are combined together to predict the socioeconomic health of these villages. Socioeconomic health is a proxy to understand the demand and ability/willingness to pay in these communities. It is actually a proxy of economic health of these villages. And based on that proxy, we actually calculate a particular score for every village, and we use that score to rank villages in this area. The output of VIDA would be villages that were identified in this area and a ranked list of the best villages to go and electrify, either using mini-grid or solar home system. Next slide, please. In step number 1, we use machine learning algorithm to automatically identify villages. Those purple dots, although only a few bigger settlements are seen here, but there are quite a large number of villages over here which are denoted by purple dots. That is automatically identified using a machine learning algorithm. Then what we do is actually we then add in grid information. The black dots that you see over here in this image represents national grid. This is a data that we did not get from the grid or the utilities, but this is a data that is derived using nightlight imagery. This is based on an algorithm that was firstly coined by Facebook. Now, what you can clearly see is on the bottom right corner and in the center towards the bottom of that particular red box, you see a large amount of area that doesn't have electricity. There is quite a large number of villages within that area. We will now zoom into a section of that off-grid area. Next slide, please. These bubbles or the purple dots that you see there actually represents villages. Now what VIDA does essentially is that it starts extracting information from each of these villages separately. Firstly, we extract information on what is the size of this village, how many people potentially live there, how many households are there in this particular village. In fact, now we have started using high resolution images to go deep into these villages to actually even count the rooftops, actually figure out the density of that particular village, and can even go into distribution planning. That is the first set of information. Now you look into those pink lines going through the village, we start extracting, what is the connectivity of this village. Now, again, the idea is to try and understand the economic health of this village, and road is an important indicator of economic health. A village which is well connected to the road, then it tends to be economically very sound. That's why we start understanding how accessible is this particular village. If it is accessible through road, what is the type of the road that connects this particular village? How far is it from a town? How far is it from a grid connected village? How far is it from a highway? The other interesting bit that we do, in fact, if you look into the village that is currently being pointed, that particular village, actually, if you see, there are two sorts of road that is going out of that particular village. These roads actually connect that village with many other villages, which means that people from those smaller villages, which it connects through road, actually flow through that village, which also means that there's a large likelihood that that village over there actually have markets, more commercial loads, and more productive loads. So, the different sort of road data is utilized to understand, hub villages or villages where there's a large likelihood of having market. Now, we also start extracting details about accessibility to water. Water is an important criteria. A village which has good access to water generally produces more and is economically sound. Those blue lines or like blue curves that you see in the image actually represents water body. We use satellite data to understand, is the water available? If yes, is it seasonal, not seasonal? We can also understand using terrain data if the water is flat, which means accessibility by boat is potentially available. So different characteristics around water is used. We also do agricultural analysis in each of these villages separately. We understand how a vitality index of each of these villages to understand if they are productive. We also do a bit of a cluster analysis. In the center of the image, in this particular slide, you actually see a cluster of villages together. These sort of cluster, where there are many villages coming together, means that there is a large amount of population to actually serve, which means you can either set up a larger mini grid or actually have multiple mini grids provide power to them. And these sort of clusters, because there's enough amount of population, generally tend to have shared large load centers, be it a hospital, be it a school, or a large number of shops as well. There's enough population for those sort of services to actually run in those clusters. So that cluster analysis is something that we do. We also look into terrain to understand which of these villages are in flatter lands, which are rather productive, or which of these villages are in mountains where the productivity slightly decreases. Again, the idea is that we extract about 10 to 15 indicators purely by analyzing satellite images. On top of that, as we go to different countries, there are a large number of GIS data that might be available. For example, there might be data around where the hospitals are, where the schools are. In some cases, we might even get data around mobile connectivity as well. So as and when these sort of data is available, we can infuse that data to the model as well. In total, from every village that you see here, we extract 10 to 15 indicators. Can you go to the next slide, please? Now what happens is we combine those indicators together using a proprietary energy modeling tool to predict what is the viability of building mini grid over here. What is the economic soundness of this particular village? We try and predict the socioeconomic health score of village, which is fairly large, has good connectivity to the road, is very easily accessible, does a lot of trade to the town, nice agriculture, productivity. These sort of villages get higher score, whereas a smaller village, which might not be very economically sound, get lower score. Here, the scores are representative, but you can clearly see the village on the right-hand side is actually very nice village to actually go with mini grid, so they are scored high. So how a VIDA can what VIDA can do for entire country is that we can automatically find all the villages, understand socioeconomic health of that villages. And based on that, we can give a rank list of the best villages to already go and electrify, either using mini grid or take your solar home systems over there. Can we move to the next slide, please? These are our different users. A government and DFIs can use our tool to actually plan off-grid electrification in their country. And most importantly, we can also use this tool to actually find best sites in the country to already tender out. We can find top 200, top 300, top 400 sites. Also, because we extract very granular data from the villages, this data can be very useful to actually allow data-driven financing mechanism like RBF or debt. Solar and mini grid companies, we're already working with some of them, can use this tool to actually identify sites where to go and build. And also for them, the tool can be utilized to find what is the purchasing capability and also plan supply chains. The investors and bank can use our tool to de-risk investment. They can also conduct due diligence using our tool. And also what our tool can do is it can aggregate sites so that their token size for investment increases. Thank you very much. Open to questions.
Thanks very much, Andres, Andreas, and Nevin for a series of very rich presentations and also being very efficient with time. So we have a lot more time for the audience to engage with us. We now have some time to field questions, and I'm going to use my moderator privileges here and get us started with 2 questions and then open it up to the audience questions afterwards. We're also seeing a few questions trickle in already, so that's great. But just a shout out to everyone to say that, keep sending your questions. So yeah, I have a 2-part question here. I think first part is I'm curious to see how all of these tools are complementary to each other and how they sort of work together. And a second part is a more practical question around how would you advise a stakeholder in the space, or let's say one of our audience members here, to take back all of what you've presented and start thinking of using these tools as soon as this webinar ends? So really sort of posing this to all of you, but feel free to start. Andres, do you want to jump in?
Okay, yeah. Well, first, I would say that we have 3 different approaches, which could very well be complementary to each other. Because for instance, our tool, we in 2013, we started also trying to follow an approach similar to KDH, but at that point we had already developed a network model, which is the reference network model, which is brother to the reference electrification model, which were used in different countries for the calculation of the distribution networks. So it was being used by the regulator in Spain to retribute the Spanish companies, or to calculate what's the least cost or the efficient cost of service for each one of their networks. And it's been used by the Obama administration to calculate the Green New Deal and all the reform that has to be done with distribution. So it was a very complex and industry model at the moment. So we decided to go through a very detailed approach, which actually, in our case, if you're trying to run a country like Rwanda with topography and everything else, it may take roughly 4 days to calculate the whole country to the last customer connection, which is a long time. So it's not a model to do a very rapid assessment, or to be able to understand the process of electrification in an interactive way, though it comes out with very detailed engineering approaches. So actually, we don't consider ourselves a geomath tool or a geospatial tool itself. We have geospatial data that is calculated through engineering design algorithms and sent back to a geospatial platform. So it's a little bit different, but I see a lot of potential in combining, for instance, the VIDA approach, where we only consider cost and we stop there. We calculate what's the efficient frontier between grid extension and off-grid and microgrids. There is a layer before and after that. One is how much is the demand that you could expect there. And on that, I find very interesting their approach of being able to determine through proxies what you could expect in different areas. And also afterwards, after you have, I don't know, in Rwanda, we have more than 30,000 microgrids to be built. So how are they prioritized? Only on cost perspective, that would be our first approach, but there are many other factors that could be added on top of that. So I find that much promising. I think that all the three tools have a lot of value. I find the work done by KDH always inspiring in many ways, and actually it's tremendously faster than ours. So I would say that ours goes for, let's say, accuracy, and they go for a very, but well, I will let Andreas talk on that regard.
Thanks, Andres. Anyone else?
Okay, yeah, I think I can follow up on that then. So I think Andreas said it very well. I mean, the tools might look similar at the first glance, but they do different things, and they have different data requirements, routing time requirements, and they provide different levels of detail in their output. So also it might be faster and easier to use to get a first grasp of the high level picture and the dynamics of different things that might happen in the future. But then once you want to go into more detailed design, you might go into REM or similar models. Similar with VIDA, they also have very complementary work to these kind of models. So you can provide important information about demands, which we saw is a key driver of which technology will be selected as the least cost technology in both of these models. And these models can also show where grid extension, for example, might be the least cost solution across many scenarios, which might mean that they're not suitable for off-grid in the analysis from VIDA. And I think for a stakeholder who wants to use these models, it's very important to start to clearly define what it is you want to know, which kind of questions you want answered, and then you start looking at which tool can best answer these questions, and reach out to the teams. We're all very happy to discuss.
Ruchi, just wanted to add, so as both Andreas and Andreas actually explained, our tools are very complementary. In case of VIDA, what we can really do is in a country which is already mapped by KTH or REM, where there is already a knowledge of villages that are suitable to be electrified by off-grid systems. That's where VIDA can really come in. Those areas which are already marked as off-grid villages can be rather analyzed using VIDA, and based on VIDA's analysis, we can really prioritize which are the best villages to already go and which are villages which might need other sorts of interventions or might need a larger amount of subsidies. So we can really feed on what is already done by both KTM and REM models. One. The second thing is also there is a very clean way of data transfer. So a lot of data analysis that is done by both REM and KTS can be ingested by us, like settlement data, like data about grade, the cost of extending the grade, many other data, even GIS data if they have already utilized. So there is also a benefit of actually already utilizing existing data and not reinventing the wheel when we combine VIDA with both KTS and REM models.
Thanks a lot, everyone. I'm going to jump right into audience questions, and we've received quite a few of them already. The first one comes I guess it can be posed to everyone on how do you determine the expected demand at this macro level to calculate a least cost solution? Andres and Andreas, I don't know if you want to take a stab at responding to that.
Andreas, can you go first this time?
Yeah, sure. So we've used a few different approaches to determine the demand. So one is the kind of top-down approach where we say, for example, that we just assign a demand, saying urban areas we think could achieve a certain level of demand based on, for example, what is the current consumption level in the country, and maybe rural areas would go for a lower level of demand, and then we can play around with this to see what happens if we go for higher or lower compared to that. The other kind of approach is more of a bottom-up approach where we try and draw on some geospatial data that can indicate which levels of demand are achievable in different areas. So there are some GDP maps, there are maps about poverty rates. We can use satellite data of nighttime lights to try and estimate which areas we think can achieve higher levels of demand and which we think needs to start at lower levels of demand.
Yeah, I would only add to that, which is forecasting demand for the future for 2030 or 2025 or whatever the year is one of the main challenges that we all face, either using top-down or bottom-up approaches. We actually favor two things. On one side, we can plan as all others according to the tiers, to sustainable energy for all tiers of service, or we usually go by something that we call natural demand, which is whatever is happening in other electrified areas in the same country. So they're having the information back from the utilities themselves or from the government to find out how the different customers consume. So maybe domestic customers by different levels of income, you could have an idea of how different households are going to consume. And also different productive customers. In the case of Rwanda, we designed the national plan for 22 different kind of customers, ranging from an airport or mineral mining down to 150 or 500 watts households, according to the different statistics of the census. In Mozambique, we dealt with 17 different kind of customers. And of course, it's not the same shop that deals in power mainly through during the day or not late at night. So you wouldn't need a lot of storage if you're providing it power with a microgrid, or a 24/7 hospital where every hour is critical and you must provide it or you must prioritize it, or a household where it's important to have electricity at 11 o'clock or at 10 o'clock or even at 12 o'clock. But maybe you don't mind so much if sometime at 3 in the night, you have a blackout every 3 days or every 5 days or every 10 days, whatever. It's the reliability level you want to achieve. So on that, we think that the devil is in the details. We also found out, and I think Andreas also mentioned before, that productive loads are essential, because otherwise, I mean, in the case of Rwanda, 52% of the customers in grid extension consume 85% of the energy. And of those, 80% are industries or productive uses. So when you have to plan a network, you really certainly need all the community and productive customers add into it. So it's we have a PhD research going on at MIT, actually looking into how to focus that into the future using AI. So to be better acquainted to when you don't have actually field work or ground data, which is most of the time in many countries, how to try to find out in the way maybe VIDA does, what is the expectation of growth of the different areas and what you could wait from them or you could expect from them based on actual data that you have from other areas. But still forecasting is always uncertain.
Thank you so much, both. Navin, I have a few questions that have been posed regarding VIDA. So one of them being that how does VIDA compare to the Odyssey platform? And does VIDA incorporate microgrid design tools such as Homer? I have another question where I would sort of love to hear from all of you, so just posing them both together in terms of are you working with or have you already worked with governments in emerging or developing countries? If yes, which countries? So Navin, if you don't mind starting here.
Absolutely, yeah. So yeah, VIDA is fairly different than Odyssey and Homer, having said that both of them are really good sort of colleagues and pals that we are now trying to collaborate with each other. So what VIDA does is that we get granular data from villages to then prioritize sites or find the best sites. And what then can happen is then those best sites can go into Odyssey platform where you can actually add more details to it. And then, you know, through Odyssey and Homer collaboration, we can really plan the mini grids for all of those prioritized villages. To summarize, we prioritize the village, feed it into, you know, Odyssey's platform, and through Homer plugin over there, we can then really plan all of those sites. So that becomes a very standardized process of prioritizing to designing the the entire mini grid plan actually. So that's how VIDA and Odyssey can work together, and we are very different actually in terms of functionalities. Yeah, so and I think, what was the second question, Ruchi? I forgot that actually.
The second question, Alvin, was around if there are countries that you're working with regarding sort of these tools, and also if you provide some support for distribution and transmission master plans for these countries.
Right. So to answer that question, we are already working with both East African, West African countries, and now we are also pitching to work in Pacific. Some of these countries, we have worked with government bodies. In some of these countries, we have already been partnering with private sector. In fact, one of our main partner till date who have also been validating our tool is one of the largest mini grid developers, and with them we have worked in West Africa actually. In terms of planning for transmission and distribution, we actually do not go to that depth of planning transmission and distribution. That is what is best done by REM and the KTS tool, and probably both Andreas and Andreas can explain that.
Andreas and Andreas, I don't know if you want to jump in and respond to that quickly here.
Well, master planning is really the challenge, but it's not the only challenge. After you have been able to achieve, I mean, let's hope every one of us is out of work in 2030 because we have achieved universal access. But then what comes next? How would quality be improved? What about all the areas with, what happens if demand grows or if the quality of service is low? So actually, for instance, in Rwanda, we are engaging in a second phase where we want to look into in detail what's happening with towns or what's happening with neighborhoods, aggregated networks in towns which are at the present level they may have a lot of blackouts, and how to deal with that. In our case, the tool is used by stakeholders in 3 different ways or for master planning. One is the master plan itself. So you decide how much, or you calculate how much is it going to take to achieve universal access, and how much is going to be grid extension or microgrids or standalone systems. But then the second use of the tool is actually how are you going to implement all those projects, so all those designs. How is your pipeline gonna happen in the next 10 years or in the next 5 years or 7 years, whatever is the scope. And for that, having individualized design is what makes that more useful. But the third is how to deal with the business models. So how are you gonna make them sustainable? How are you gonna help microgrid developers or not to work in certain areas? Because one important thing is that rural electrification is expensive. It's much more expensive than electrification downtown, 10 times, 5 times, 20 times more expensive. And it needs some kind of subsidies, or else people would have to be happy with consuming 20 times less or 5 times less than the equivalent people with the same income in the cities. So how do you deal with that? How do you deal with what's the efficient cost of a certain system in an Andean region or in the middle of the Amazon? And how are you going to plan that people is going to pay a tariff or an open market fee, and how they can afford it, and whether the country or cross-subsidization can step in. So the third way in which REM is important, and I think other tools here as well, is to determine what's the efficient cost of service and how much is the subsidy required, individualized per system or overall for the country, that would take the system running at the end. Because otherwise, we are going to only electrify those areas where they can afford it, and we are going to leave behind everyone which is below a certain level of income, and they cannot afford the system, or they can just afford a lantern. And they are going to stand with that for years, which is not the purpose of what we do.
Thanks, Andreas and Navan. I'm going to take one more question and then really sort of hand it over back to the panelists to provide their closing remarks. So one of the questions that came is around data sensitivity. So the question I have is that, do these models rely on publicly available data? For instance, onset developers have published several papers focusing on the use of publicly available data. Do REM and VIDA do this too? For example, how sensitive it is to census data and its granularity, or to existing network layers. So really sort of if you can respond quickly to this one. Thank you.
Hi, Ruchi. Probably I can answer that question. In case of VIDA, we do not necessarily rely a lot on public data. One of the main reasons why we rely on satellite data and extract most of our information from satellite data is to go around public data, because we have realized that, especially if you go into remoter part of the world, the quality of data keeps on decreasing, and making a very important decision utilizing that data might be detrimental. So we try to use as less public data as possible. Having said that, there are a few bunch of data which is very high quality. One of them is the Great Finder data that has recently come out from World Bank. I think the GSMA data that George and the team have actually come out with is extremely high quality data as well. So there are a bunch of high quality data that we can already use, but utilizing something which is randomly available there can be detrimental.
Thanks, Navin. Andres and Andreas, I don't know if you want to sort of jump in and react to this as well.
Yeah, so I mean, as I think most of us here know, accessibility to good data is really key to get good modeling results. So we try and use public data, and we're really happy to see these initiatives that we've heard of, such as Grid Finder and so on, that can use different algorithms to produce the data whenever it's not available. But we're also, of course, hoping that more and more people will make data available, because we know that it's out there, so that it can be used to inform these kinds of analysis.
Yeah, true. Only adding, I mean, public data is scarce in some countries, and I think the effort of improving that worldwide is the only way in which the kind of analysis for content that KDH has done in the past is feasible. We always use an approach, a mixed approach, where we use the best quality public data that is available and mix it with whatever private data that we can find about consumption levels, about the use of energy, or about real location of high voltage, medium voltage, and low voltage networks, which in some countries is there. And in other countries, you just have a picture of whatever the medium voltage was 3 years ago, and you have to manage with that. Or you can use your own estimations based on the location of the customers. So then the third is assumptions, or is enriching or geo-enriching whatever data you have in order to achieve the most accurate starting point with which to work. And then, of course, you need to run sensitivities around those initial data to cover your ground on how much uncertainty would affect the results. So if the demand is higher or lower than you expected, reliability is higher or lower than you expected, or the cost of energy from the central network is this or that, or in 30 years, how much is going to be the cost of batteries, or how much is going to be the cost of panels. All that is, I mean, brings a lot of uncertainty to any master plan. And actually, you need to find the most probable scenario, and then also have some advice of how to deal with deviations from that. So to follow it through. So for me, the important thing is not having a map and delivering to someone, but delivering him the tools so he can update and upgrade the map after monitoring what is happening in the country in the years going by.
Thank you. We're out of time now, but if we can please take 5 more minutes to have the panelists provide the closing remarks. Just a quick note that we will be sharing both the presentation and the recording of the webinar with everyone. Also, please keep the questions coming via our social media handle or email, and we'd be happy to liaise with the panelists and respond and get back to each one of you. So going around the table again, starting with you, Andres, if you can just sort of provide your closing remarks very quickly. Thank you.
Yes, well, I think that the first message that we want to put there is that we need to be daring, and we need to think about solutions that are up to the challenge, of which the 3 ones here are very good examples. And we are not going to achieve universal access in 2030 unless we accelerate a lot. And that's what, for instance, we started proposing in New York in the last summit of United Nations, that we need a framework in which governments, companies, and NGOs and international agencies work together in the countries to achieve this and enabling frameworks. These tools can help a lot in estimating how these frameworks could happen, but we do really need to accelerate. Otherwise, we're going to help, we're going to be useful, but we won't be able to get universal access done.
Thanks, Andres. Andres, do you want to go next?
Yeah, sure. So, I mean, thank you all very much for attending and for posting a lot of questions. It's very, very nice to see the interest.
Thank you.
Use these tools, go around, see which one fits your purpose best, and they can all provide different information that can lead to better decision making, and they really are complementary. So have that in mind. And feel free to reach out to us if you have any questions. Thank you.
Thanks, Andres. And Navin?
Likewise, actually, there is a large amount of benefit that we can generate if all of us actually sync and collaborate and try to generate a pool of data that is useful to actually generate decisions or data-driven decisions. There is very little known about these remote villages that needs to be electrified before 2030 in order to achieve SDG 7. And we, all three of us, are really trying hard to actually generate a lot of data from this village and allow decision making through these data. We would be very keen to actually get your feedback as well. A lot of you in the audiences are, are folks who have been working in emerging markets, are folks from there. So it'd be really good to hear your feedback, also to understand if our methodologies or our processes would do the job. That'll be one thing. So our emails will be here. Apart from your questions, we would look forward to getting your feedbacks as well. And at the same time, if you could also, talk about our tool in the market, that would be really useful, because I think the time has come for people to really understand that there are tools like ours who can shed light on these remote villages as well. And thanks a lot, Ruchi and the team, for organizing this webinar. It has been really great.
Thank you, everyone. I keep this very short, but really want to extend thanks and gratitude on behalf of the Mini Grids Partnership and Sustainable Energy for All to all our panelists for participating today. I think all the presentations demonstrated the depth and width of the extent of these tools available in the market, but also the effort that you and your organizations are placing on this issue. So final thank you also to all the participants who took out the time to join us for the webinar today. Thank you very much. And as I said before, we will be sharing both the presentation and a recording of the webinar very soon with you. Thank you.